discussing a presentation by Dan Bauer. He's at Fermi Lab. He's talking about the mystery of dark matter. And the reason we want to talk about this is several-fold. One is just pure academic curiosity. But it's also important to notice that we believe that the mystery of dark matter is sort of in the same family like the black body radiation at the end of the 19th century. Which led to the discovery of quantum physics and really changed the 20th century. And we believe that as quantum physics is at least on the verge of getting to some sort of maturity and commercial applications beyond semiconductor, which is already big, but we're talking, quantum information processing, this idea that energy systems are quantized, has a lot more legs to go. But dark matter is the new mystery, the mystery of the 21st century. I mean, it's been around for more than just a century, but we believe that we are on the verge, hopefully, of getting solutions maybe in the next decade or so. And the beauty about this is it's a nice example of how science works. It's a nice example of how physics works. And it's also important to understand how knowledge creation works. And that's why what we do here at Orange Capital Partners. This is the podcast series, the Not Even On podcast series, is about knowledge creation. It's about wealth creation, which is actually the equivalent of knowledge creation. There's no wealth without knowledge. There's no knowledge without wealth. So all these things are intertwined. We've spoken about this many times. Wealth creation, freedom, and knowledge are all parts of the same thing, just in different manifestations of the same thing. There's other words for it: progress, liberty, self-expression. All these kinds of things are related to these concepts. What we want to talk about here is this particular presentation. So we'll focus on dark matter and its intricacies and the detection and the technologies and the answers and the questions and the answers that go with it. And the prelude here is meant to just give people a sense for why we're doing this. So we're not going to discuss the whole idea of knowledge creation and epistemology that are attached to this type of reasoning. We're going to focus on dark matter and Dan Bauer's presentation, but I just want to make sure people understand why we're doing this here at the Not Even Wrong podcast. This is the Not Even Wrong podcast. It's September 10, 2024. This is Krim Delko. It's the second installment today. We are up 7.6% for the year. The market's up 15.7%. We're underperforming by 8.1%. So Dan Bauer from Fermi Lab gives a presentation a couple of years ago now about dark matter. Highly recommended. Links in the show notes. It's a very approachable presentation. It's not popular science. It's science, but it's approachable, and that's obviously that's the bikini test for IQ and science and an ability to do research. So a person that can explain difficult concepts like dark matter, in my opinion, has also a chance to contribute scientifically. So let's start with dark matter. First, it's the wrong name, actually. It shouldn't be called dark matter. It should be called transparent matter or invisible matter, because dark matter is just matter that absorbs all kinds of light and therefore is visibly dark. But that's not what dark matter is. It's actually invisible because it does not interact electromagnetically with any matter that we know. Now, why do we think it's out there? There's two main reasons. There's a couple more. The two fundamental reasons. One is orbitals of planets show certain mathematical relationships that can only be explained if there is more matter than the one that we can actually see. Now, from there, we infer that dark matter actually feels gravity, so it has gravitational attractions and repulsions, and therefore has this effect on orbitals of planets. There's the other thing that happens in cosmology, which is gravitational lensing. That is the idea that when a star shines from far and the light passes a large galaxy, again, with lots of stuff in there, then that light gets bent because of gravity, because stuff has gravity. And the bend of light, the redshift that we can see in the light coming from stars going through, let's say, the Milky Way or passing by the Milky Way, is much larger than what we think it should be based on the matter that we can see, and therefore we infer that there is something else, again, dark matter. So how do we detect this thing? Now, this is, of course, the difficult thing, because now you're looking at seeing something that you can't see. And the way you can do this is there's two fundamental ways to do this. Well, one is you can try to see it by developing better technology that allows you to see something you weren't able to see before. For example, the electron microscope was developed because we were able to granularly reduce or increase the resolution of basically what microscopes were, which is advanced photographic instruments, to the point where we can actually see down to the electron level. I would say, recent Nobel Prizes in physics about, I believe it's called picophysics, or like we can see at a time scale, a billionth of a billionth of a billionth of a second. That means just we have technology that allows us to see in more detail than before. And the same concept is now applicable to dark matter research, which is, well, we just can't see it because we don't have the right lenses for it. Let's build them. So that's one thing. Now, how is this done? The presentation actually goes over some of the technologies there. And the fundamental idea is that you want to be, first, of course, you want to isolate every possible noise that you could possibly have, and have something which is highly sensitive to energy levels, but is not affected by anything else. Now, of course, that's incredibly difficult to do, but that's the idea, because you might then think, okay, look, we have this very low energy thing, which is like matter, but we can't see it. We call it dark matter, but it does interact with something, let's say, that interacts with xenon, let's say, a noble gas. That's one way to try to detect it. There's other ways to detect it, where nuclei or certain uranium isotope nuclei have particular properties that could be used to interact with dark matter. So that's one way. So again, we could develop substances, sensors, if you will, to detect it. The other way is indirect detection, which we already kind of have, right? We have a quantized way. We can quantify, a quantified way. We can quantify that there's something out there that's called dark matter, but we could maybe find better ways to measure things we can see that might be affected by dark matter, and then infer from there at least the properties of dark matter, right? What we're trying to do here is, of course, get to the gist of it. What is it? What is this thing? And if we have the properties, we can then build models and better observe, and then maybe eventually find something that fits a theory that we have about it, and then combine it and say, okay, this is dark matter, right? Now, I mentioned the theory, so we have theories like WIMP, weakly interactive massive particle. That's one approach. Axion's another approach. Then we have neutrinos, which are kind of like dark matter, but they're detectable, but they're not energetic enough to, there's not enough of them, excuse me, to explain the other effects. So this can't be the only, maybe it's part of the dark matter family, but it's definitely not the whole thing. So again, so we have a couple of candidates of what it could be. And of course, the hope is that as we get better at detecting it, we might also be better at modeling it. Now, why do we want to understand? Why do we want to understand this? So there's three reasons that then cites. One is we want to understand, particle physics better. We want to understand cosmology better, and we understand astrophysics better. And I find this really interesting, because just by explaining how dark matter will help us, he's also giving us a definition of what these fields are, which for a lot of people, for all of us from the outside, is not so clear. So, for example, what is particle physics? Well, it's trying to understand how the elementary particles known to mankind actually behave. Elementary particles or the standard model of physics, which is based on the four forces: the weak force, the strong force, the electromagnetic force, and then gravity. Now, the standard model explains three of them. It doesn't explain gravity. I don't want to go into that. I'm just saying here that with the approach to dark matter, we could get a better explanation of how elementary particles actually work, what they consist of. Maybe we can expand the standard model to a different type of matter that we haven't known until now because we haven't seen it. It wouldn't be the first time in the history of mankind, right, that we've discovered something and then we've been able to change the model. I mean, we've discovered that the world is not flat, and that gave us an idea of what the universe looks like. And we've discovered species that helped us understand evolution. So by looking better, by seeing more granular, by seeing more focused, we can develop new ideas. So I think that's one thing. So we can help with the standard model of particle physics. Dark matter can help us there. Dark matter can help us in cosmology. How can it help us in cosmology? Well, it might be able to explain to us the formation of galaxies. There's a conjecture that dark matter is the ultimate driving force of the consistency of galaxies and Milky Ways and things like that. Again, Dan Bauer explains why we believe that. There's certain models that we use. The idea here is that you have a theory, and then you model in a supercomputer, you model the evolution of the universe based on that theory, and then you look at what you actually see, and there's a lot of overlap. So you believe that you're on the right track. So again, in cosmology, dark matter would help us understand the formation of, let's say, why does the universe look the way it looks? What are the driving forces behind it? And in astrophysics, it's more, astrophysics is more like maybe geology, like what's out there? Okay, how much dark matter is there? How much matter? What's the relationship between matter and dark matter? That's, think of it like more like, okay, what's going on? I equate astrophysics with geology. So the same way geology is like, okay, what's out there in the earth, right? What are the relationships between tectonics and rocks and all that stuff? Here it's just the same idea, but in the astro world. And of course, in the astro world, we're talking a lot about electromagnetic waves, light, things like that, but also matter. Now, what's most astonishing, just to be clear for people that might not be familiar with this, right? What the dark matter research tells us, and that's, I think, very hard to contest, is that what 5% of the universe is matter, stuff that we actually see. 95% is dark energy and dark matter, different things, let's not even go there. But dark matter, again, so there's stuff we can see, that's 5%, and there's stuff we cannot see, which is about 27%. And then there's dark energy, or something else. That's what's out there in the universe in terms of stuff, which is calculable through approximations of, given our theories of astrokinetics and general relativity and things like that. That's how we fit the models to work. Now, of course, general relativity could be completely wrong. And I think what this alludes to, and this will be my conclusion, this is why I wanted to talk about this presentation. I think that we are on the verge of a completely new understanding of physics. And I think the door will be opened by the research in dark matter. My son is 17 years old. He's just finishing high school and hopefully will embark on a physics career as a scientist. And he is actually working already on a project with dark matter. And I believe that there's a good chance that that could be a really fruitful career. That if he focuses on dark matter, that he will not just have an interesting scientific career, but really make some massive contributions to humanity. So now let me finish by just giving people a bit of a sense for what this all means for us. I mean, again, we're a hedge fund. Orange Capital Partners, mission of Orange Capital Partners is to generate wealth by investing in fundamentally new concepts and engineering practices. So why are we talking about dark matter? Well, obviously, we are interested in knowledge, in particularly scientific knowledge, scientific progress. We're interested in knowledge creation because we equate that with wealth creation, right? And I think this is a beautiful example of a new frontier in science that will eventually yield massive, massive returns for humanity, because it will open up our eyes to a whole new world. I'm 100% convinced about this. The parallels to black body radiation are just obvious, right? I mean, you can see them. We're measuring stuff. We can understand it with our existing theories, but we're seeing it, we're feeling it. We know it's there. We don't know what it is. We will keep searching, and we will find an explanation. This is David Deutsch 101. Right? We will find an explanation, and that explanation will open up doors to whole new worlds and better technologies, and hopefully serve humanity to the positive. Thank you.